In the last video, I examined the ASDA blackweb power bank that on the first glance did not meet the promised battery capacity, like so many complaints you find on this topic on the internet. Undoubtedly, there are lots of cheats and dubious products out there, but to my surprise, I found at least in this case the problem was simply a misunderstanding of the math and physics involved and no cheating was going on. I thought it might be worth a short follow-on video just focusing on the question of true battery capacity in USB power banks. As a quick recap, one of the things I measured on the ASDA blackweb power bank was its promised capacity of 2600 mAh as written on the box. After charging the power bank until it indicated full, I connected an electronic load to the USB port, set the current to constant 1 amp and let it run until the power bank shut itself down about 1 hour and 30 minutes later. 1.5 hours of 1000 mA current meant I got a meager 1500 mAh out of the supposedly 2600 mAh battery. Yet, when I disconnected the battery, one of these ubiquitous 18650 lithium cells made in China, and ran it through a similar discharge cycle of constant 1 amp, I found it was pretty much spot on in meeting its promised capacity. Repeating the discharge cycle from the USB while tracking the USB voltage and current as well as battery voltage and current reveals this strongly symmetric graph. The dotted lines are the USB measurements, while the solid lines represent the battery values. In both cases, the current and voltage plots over time are mirror images. Although for the USB case, both are of course pretty much just flat lines. The mirror images are caused by the fact that what we're really doing here is extracting energy as power over time from the battery and delivering energy to the load of the USB port. Power is the product of voltage and current, and if the power demand remains constant but the voltage drops, as in the case of a battery, the current has to rise to make up for it. To explain the missing capacity in another way, consider this little diagram. The power bank's USB port is used to provide 1 amp for 1.5 hours, which means a total energy demand of 7.5 watt hours and a capacity of 1500 milliampere hours. Assuming the boost converter in the power bank works with 80% efficiency, which is probably about right for most power banks, it will need to get 9.4 watt hours of energy from the battery to deliver the 7.5 watt hours on the output. The 1.9 watt hours difference are lost as heat in the conversion process. So the battery has to deliver 9.4 watt hours of energy to the converter. We know that the voltage of the battery is not constant and will drop slowly from 4.2 when full to 3 volts when empty. But we can use an equivalent constant 3.5 volts as average over the whole period. To deliver 9.4 watt hours from an average of 3.5 volts needs 2685 milliampere hours of battery capacity to sustain an average current of 1.79 amps over 1.5 hours. And there you have it. We've just got 1500 milliampere hour capacity out of a 2600 milliampere hours battery, a meager 57% of what was in the battery, and no cheating was going on. The key to the problem is, of course, that capacity only looks at current over time and implicitly assumes that the current goes directly through the consumer, while the voltage across the consumer is always identical with the battery voltage. For anything with a buck or boost converter, such as USB power banks, this is simply not the case. The apparent loss is the price you pay for a higher constant output voltage. Incidentally, the problem is not the 80% efficiency of the converter. That makes it worse, but even with 100% efficiency, we have the same issue. With 100% efficiency, the 7.5 watt hours from the USB translate to 7.5 watt hours demand from the battery, which needs a capacity of 2142 milliampere hours. That is still substantially more than the 1500 milliampere hours that we get at the output. So, as a public service, this chart offers an answer on how much of your battery capacity can you expect on the USB side. This depends, of course, on converter efficiency, but as you can see, even at 100%, we can only expect 70% of the quoted battery capacity at the USB output. In most power banks, I would expect the converter to run at 70 to maybe 90% efficiency, which would translate to a USB capacity of 50 to 60% of the battery capacity. To verify this, I tested the 3 power banks I could find in our house. All 3 are rated 1 amp max on the USB port, and I discharged them at a constant 1 amp. The ASDA blackweb is quite new, although through my tests it has probably accumulated about 20 complete charge and discharge cycles. It has a verified battery capacity of 2600 milliampere hours. The smaller TextNet PB2000 is probably around 1 year old and has seen only occasional use. The stated capacity is 2000 milliampere hours. The TechNet IE380 is several years old and was used mainly during holidays. Apart from probably using older converter technology, the battery is probably starting to wear out. Its stated capacity is 5000 milliampere hours. Admittedly, this is a very small sample size, but the results appear to confirm the finding that one can expect only 50 to 60% of the stated battery capacity to be available on the USB port. The Texas PB2000 seems to have either a better battery than claimed or a very good converter to achieve 64%. There's an interesting twist in this matter that is hardly mentioned anywhere. While many complain that their power banks fall short in delivering the promised battery capacity, hardly anyone seems to notice that they also seem to take less capacity to recharge. The reason is of course exactly the same voltage difference effect, except that things are now in reverse. The circuitry in the power bank now runs a buck converter to reduce the 5 volts from the USB port to charge the battery. The only difference is that the USB port tightly constrains the amount of current the power bank is allowed to draw, which means the overall effect is less noticeable. Here are battery voltage and current for the ASDA blackweb power bank when charged from the USB port. The USB current is not shown and was always less than the battery current and never exceeded 1 amp. The capacity going in on the USB port for the whole charge cycle was 2379 milliampere hours, while the battery capacity calculated as the area under the red curve was 2605 milliampere hours, as you would expect, because LiPo batteries are generally very good and operate with 95 to 99% efficiency. In case you're wondering what happened, on the right side here, I enlarged this part of the graph. What happened is that the charge circuit decided 3 times that the battery was full, cut off charging, and then immediately changed its mind and resumed charging. Only after the 3rd time did the charge remain off. I had not detected this earlier, and it's very easy to miss as the events take only seconds. I'm wondering if this is by design to improve the overall amount of charge. It seems too regular, and certainly on the whole the trend of battery voltage and current continues during these events, so the battery was indeed not full yet. By the way, the battery current drops not down to 0, but actually negative 7 milliamps or so, because the power bank powers its bright 4 LED state of charge indicator directly from the battery. Somewhat naughtily, the LEDs stay on as long as the circuit detects that a charge cable is plugged in, even if there is no more current flowing. So counterintuitively, you are now actively discharging the battery while it's still plugged into a charger. If you want to know more about the quirks of this power bank, you can watch my earlier review and teardown of the ASDA blackweb power bank. This table here shows the capacity values measured on the USB side while charging the 3 sample power banks from empty to full. As you can see, on 2 of them the effect is noticeable. The TechSet PB2000 seems again to be the odd one in taking more capacity to charge than the battery rating. The reason could be a terrible buck converter or, again, a higher battery capacity than stated. If it is using a bad converter, I would expect the power bank to get quite hot during the charge because the excess energy has to go somewhere. As this is not the case, I suspect that the battery in this power bank is better than the advertised 2000 mAh. One of these days I may get around to actually open up to check. No doubt that there are non-reputable sellers pushing power banks with overhyped capacity and second-rate batteries. But as I try to show in this video, even good power banks simply cannot deliver the quoted battery capacity in full on the USB port. If you get 50 to 70% of it, the power bank and battery are working fine and as they should. Thanks for watching.